All right. Almost dad's time. Let's get started. Welcome to business. Just a reminder to everybody, not that we meet on Mondays, but there's no class on Monday, right? It's a 3-day weekend, so don't come to class on Mondays. None of us will be here. So let's go ahead and get started. Today is the 22nd. So there was a request to do a couple more linearization problems, and I want to point out that when we were doing this on Tuesday, I was kind of showing you what I think of as the kind of best or easiest way to do it. Meaning, if someone said, just for example, if I said to say like approximate or estimate the square root of 9.3, the function you would all use is the square root of x. So typically, we would use f of x equal to the square root of x. Our a value would obviously be 9 because that's the number that's close that we're going to plug in. And then our linearization would be f of a plus f prime of a times x minus a. A is 9. F of a is the square root of 9, which again should be easy to evaluate. And f prime of x is 1/2 x to the negative 1/2, which I like to write as 1 over 2 times the square root of x. And so f prime of a is going to be 1 over 2 times the square root of 9, which is 1/6. So subbing that all in here, we get the very kind of nice equation of the tangent line, or the linearization. L of x is 3 plus 1/6 times x minus 9. And then if we wanted to approximate the square root of 9.3, we'd say, okay, the square root of 9.3 is approximately L of 9.3. And then we get 3 plus 1/6 times 9.3 minus 9, which ends up being, I don't know, 3 plus, that's going to be 0.3. 0.3 divided by 6 is, well, 3 divided by 6 is 1/2, so 0.3 divided by 6 should be not 0.5, but 0.05. That's going to be 3.05. And that's the way you should do it if they don't give you the function already. However, there are some Weber problems where you can't just do it so easily because they try to make it a little bit harder than it needs to be. So let's look at the same example, but from a different lens. So instead, we're going to start off by saying, we're going to let f of x, they're just going to give us a function. Let's say it's the square root of, what do I want to pick here? Sure, let's say it's the square root of 9 plus x. So instead of finding the linearization of this at x equal to 9, like in the previous problem, we're going to start off by finding the linearization of f of x at, instead of a equal to 9, it's going to be a equal to 0. So we're still kind of getting a good approximation of the square root of things that are close to 9. because we're going to have square root of 9 plus 0. So to do this, usual process. Our linearization is still just f of a plus f prime of a times x minus a. But now things have changed a bit. My a is 0. My f of a is the square root of 9 plus 0, which is still 3. And my f prime of a, well, I have to find f prime of x first. So the derivative of 9 plus x to the 1/2 is 1/2 times 9 plus x to the negative 1/2. And then we should be thinking about the chain rule here and multiplying by the derivative of the inside stuff, which is just 1. But I would always say if your inside stuff is any more complicated than just x, you should be thinking about using the chain rule, multiplying by the derivative of the inside stuff, even though it's 1. And then I like to rewrite this as 1 over 2 times the square root of 9 plus x. And then if we plug in our a value, which is 0, f prime of a is going to equal 1 over 2 times the square root of 9 plus 0, which is also 1/6. So we kind of almost get the same linearization. We have the same y value, we have the same slope. But here's what the equation is going to be. Our equation is going to be L of x equals f of a, which was 3, plus f prime of a, which is 1/6, times x minus a, and a is 0. So essentially, we have the same situation about these problems. It's just that this one here has been shifted, 9 to the left, I think, compared to that one. That's all that's really happening. And this tangent line here is exactly shifted 9 to the left from that previous one. So now here's the question. I want to use this linearization. Use the linearization to estimate or approximate the square root of 9.3. And this is where you have to kind of do a little bit of undoing here. Say, well, if I'm trying to estimate the square root of 9.3, I'm not going to plug in x equal to 9.3 because I need to know if I want the insides to be 9.3, x needs to be just 0.3 here. So to estimate that, the square root of 9.3, if I wanted to be really explicit about it, I could actually just write it as the square root of 9 plus 0.3 and say to myself, okay, that 0.3, that's the x value that's going into my function. So that's the x value that's going to go into my linearization. So we're going to get that's approximately equal to L of L of what? Not L of 9.3, L of 0.3. Because, and all I haven't said here, we're saying that the square root of 9 plus x is approximately L of x, which is 3 plus 1/6 times x. So then we're going to plug in our 0.3 and get the same thing we got before. 3 plus 1/6 times 0.3, which is still 3.05. We'll do another one without all the buildup. So, let's see, what else? Yeah, sure. But I'll say the marked difference between doing it this easier way and doing it this harder way is the harder way usually stems from them telling you what the function is in the first place. If they don't, you can usually make it easier on yourself. So let's look at another example. So let's say we want to approximate, sorry, I should start off, sorry, we're going to approximate the cube root of 8.4 using, now I'm going to pick something really kind of bizarre, using f of x equal to the cube root of x plus 5 as my function. Just to be terrible, really. There's no good reason to use this function, other than that's what the person writing the problem decided. All right, so we're going to find our linearization first. So I should say, when I do these problems, and I should have said here, approximate the cube root of 8.4 using a linearization of f of x equal to the cube root of x plus 5. So general usual setup, right? We're always writing our linearization is f of a plus f prime of a times x minus a. Now, I want you all to think about for a second what value of a, don't say it, think it. What value of a do we want to be inputting here so we get an output that's close to that but is easier to calculate? When you think you know it, show me on your fingers. There should be a number you can show me on your fingers. So close. Yeah. Yeah, we want to be plugging in x equal to 3. We're going to get an output of 2, right? But if 3 plus 5 is 8 and the cube root of 8 is 5. So in this problem, we're going to use a linearization of f of x equal to the cube root of x plus 5 at a equal to 3 to be super duper annoying about it. So then after we've identified the function and the a value, we can write the linearization. So let's find the derivative first. So let's find the derivative. So our function is x plus 5 to the 1/3 power. Our derivative is 1/3 times x plus 5 to the 1/3 minus 1 is negative 2/3. And then we multiply by the derivative inside, which is 1. And then f of a is going to be 3 plus 5 to the 1/3 power, or the cube root of 8 is 2. And f prime of a is going to be 1/3 times 3 plus 5 to the negative 2/3 power. Okay, I would rather think of this as 1 over 3 times 8 to the positive 2/3. That's going to be 1 over 3 times the cube root of 8 is 2, but I still have to square it. So it's 1 over 3 times 4, which is 1 over 12. There's my slope. There's my point. So here's my linearization. L of x equals f of a, which was 2, plus f prime of a, which is 1/12, times x minus a, which is x minus 3. Okay. So now for the end of the problem, to approximate or to estimate the cube root of 8.4, we are going to say f of some number equals the cube root of that number plus 5, and it's going to be approximately L of whatever that number is. And we have to figure out what goes in here so that we can approximate the cube root of 8.4. I want you all to think about it and fill it in. So all those underlined spaces should be exactly the same number. Where do I keep hiding my water from myself? I'll write that. And how, oh no, I'm crazy. Saw something that looked crazy to me for a second. Sorry. Just fooling myself. All right. We know we want to end up with the cube root of 8.4. So I need to have what number going in to add to 5? 3.4. Because 3.4 plus 5 will give me 8.4. So I need f of 3.4 to be approximately equal to L of 3.4, which is then going to be 2 plus 1/12 times 3.4 minus 3. It should make some amount of sense. It's not sensible to do it this way. This is like the weirdest way you could do it. But what I think should make sense is that when you plug this in, this difference here should always be relatively small, right? The delta x here, the change in your input, shouldn't be very large. So if this difference here is bigger than like 1, you probably have picked the wrong a or the wrong x to put. So this is always supposed to be small because we're saying, well, we're pretty close to 8.4. So our output should be pretty close to the cube root of 8. 2 plus a little bit, not a lot. Let's see what we get. So this is going to equal 2. Well, that's a terrible pen. Going to equal 2 plus 1/12 times 0.4. If decimals are not my favorite here, but here's what I'd probably do if I was trying to make this look nicer. I'd probably rewrite this as 2 plus, I'd multiply, instead of saying 0.4 over 12, I would think of this as 2 plus 4 over 120. Because 4 over 120, I'm just multiplying the top and bottom by 10. And then I can think of this as 2 plus 1 over 30. You could leave it like that. You could write it as 61 over 30. That's also fine. I find this not very helpful. Like, this doesn't help me see that I'm close to 2. I think writing like this is great. Or you could use a calculator. Yeah, a calculator. I feel like I should know what 1 over 30 is, but I don't. It's probably 0.0333 forever. Let's check. 1 divided by 30. If my calculator says something stupid like 1 divided by 30, I'm going to be really displeased. No, it's 0.0333 forever. So, or you could say it's 2.033 forever. Just to compare, what is the cube root of 8.4? Let's find out. 8.4 to the 1/3 power is 2.032. Okay, so actual value, cube root of 8.4, approximately 2.03279. Pretty good. Not bad. So this is kind of silly to do it this way because I feel like we've come up with kind of the weirdest way of doing it. But again, if you're given a problem in web work typically where the function isn't like the nice thing you would do, then this is what you would do. In reality, the way you would actually do this is you would say, yeah, my f of x is the cube root of x, my a value is 8, and then I'm going to plug in, my a value is 8, yeah, and then my f of 8.4 is going to be approximately L of 8.4 after you find the linearization. That's like the more normal way of doing this problem. Questions about any of that? Kind of weird. I don't really know why web work. I don't know why you would do it this other way, but other than to make you practice doing things in a weird way. Okay. Who has a test tomorrow? Few of you. Okay. So not that we're going to do review necessarily all day, but just a quick kind of survey of you, the 4, 5, 6 of you. Is there anything really on your mind about your exam tomorrow? Is there anything really pressing that you would like to see maybe one more example of? Yeah, Kat. Related rates. Okay, it's always good to review related rates. So let's look at a related rates problem. Yeah, let's do one of those. So here's a classic. A 6-foot tall person walks away from a 20-foot tall street lamp at a pace of 4 feet per second. How fast is the length of their shadow changing? In any related rates problem, you almost always need to draw a picture. So let's draw ourselves a picture. We've got our street lamp over here, shining bright, and it's a height of 20 feet, and that height is not changing, so we don't give it a variable name, we give it the numerical value it is, it's always 20. And then over here, some person who is 6 feet tall, and they're walking away from the street lamp, so they're going that way. And then we also care about, well, I should say, let me label how tall they are. They're 6 feet tall. And what we care about is how this length, specifically how this length is changing. So since that is a length that is changing, we're going to give it a variable name. I'm going to pick y. And we also know that they're walking that direction, so the distance between that person and the base of the lamp is also changing. So this distance here, let's call that x. A reminder that things that are changing, you want to label with variables. Things that aren't changing, you want to label with their numerical values. And although I could mention the length of this light being cast, I'm really only interested in the things that I know about and the things that I'm being asked about. I'm being asked how fast the length of the shadow is increasing. I'm being told how fast the person is walking, aka how fast the length of X is changing, or the distance between the person and the stationary object is increasing. So after we've drawn our picture, then we usually like to write down something like, what are the things that's changing? And how is it changing? So we know X is increasing. We know that the rate of change of X, dx dt, is equal to how fast the person is walking, right? We're moving 4 feet every second. So X is increasing at a rate of 4 feet per second. And then we want to know how fast the length of the shadow is increasing. I forgot one. Well, it didn't actually, but I should point out, I technically, if you read this problem right now, you might think there's not enough information to solve it. Bless you. So I'm going to say one more thing. How fast is the length of the shadow changing, comma, not question mark, when they are 15 feet from the street lamp, 15 feet from the base of the lamp. So when X is equal to 15, how is the length of the shadow changing? At what rate is it increasing? Okay, so we've listed all the things that are changing that we care about or that we want to know about. And now we have to have an equation relating all of the things that aren't time. So we need an equation relating X and Y. This is not a Pythagorean theorem situation, even though you got right triangles. So typically with right triangles, it's either a Pythagorean theorem kind of deal or it's a similar triangles kind of deal. This is a similar triangles kind of deal. So what we're going to say is, if you look at this, if you just draw like the triangles, you've got this bigger triangle whose height is 20 and whose base is X plus Y. And you've got this smaller triangle whose height is 6 and whose base is Y. And you can set up any ratio you want. I would encourage you to pick one where the variables aren't in the denominator. So if I was going to set up an equation here, I'd say, cool, the base divided by the height is equal to the base divided by the height. Or alternatively, if you really like trigonometry, you could say that this angle is theta, this angle is also theta, and cotangent of theta, which is the adjacent over the opposite, should be the same for both of these triangles. So both of these things I just wrote are equal to cotangent of whatever the angle is. Really, that's how similar triangles always work, is it's just some trig function of some angle equals the ratio of one side to another, and it's the same in both triangles. So now, before I take the derivative of both sides, I could make my life a lot easier. I could multiply, well, I could cross multiply. I could say 20 times y equals 6 times x plus y. And I could even say 20y, I could subtract 6y over equals 6x, so that 14 times y equals 6 times x. I could have gone further. I suppose I could have divided both sides by 14 if I really wanted to. So here's our equation. Our simplified equation is y equal to 6 over 14 times x. So now Let's differentiate both sides. With respect to time, right? It's always we're taking the derivative of time. So why don't you all take the derivative of both sides of this equation and see what you get? You shouldn't get 1 equal to 6 over 14. There should be some dy dt's or some or some dx dt's in your derivative of both sides. All right, that's what I got. Dy dt equals 6 over 14 or 3 over 7 times dx dt. And now something curious is going to happen. We're going to plug in the things we know and solve for what we don't. And I'm going to plug in dx dt equal to 4, and there's nowhere to plug in x equal to 15 feet, which is kind of unique. That doesn't usually happen. Usually it matters how big the circle is, or how much volume is in your cone, or how far away from the lamp you are. But it doesn't actually matter here. You could be 15 feet away or 30 feet away, and the rate of increase of your shadow's length is always going to be directly proportional to just how fast the person is walking. Doesn't matter how close they are to the lamp. Assuming, again, the light could like extend forever and you could walk as far away from it and still have a shadow. Right, it's okay, not realistic, but that's the idea. So here, we're just going to say after we plug in, we're going to get, all right, so dy dt is what we're trying to find. So dy dt is equal to, I'm going to reduce that fraction to 3 over 7 and multiply it by my 4 feet per second. So I end up getting 3 times 4 is 12 over 7 feet per second. And that's how fast the length of the shadow is increasing. Now, oh, question, yeah.
So when you're given like find a blank.
Yeah, I think I know. Yeah, yes, maybe. I think so. Yeah. I don't have a photo, but yeah, I think I can. I think I can make something up. Let me. Yes, yeah, yeah. Let me say one more thing about this though. So I'll point out sometimes this question gets asked this way, where they ask you how fast the length of the shadow is increasing. An alternative way of asking this was just asking for something slightly different. Is we could also, or I could say we could ask, instead of how fast is the length of the shadow increasing, how fast is the tip of the shadow moving? Or what is the speed of the end of your shadow? And that's a different answer. Because if you think about it, looking back at our lamp picture over here, if your shadow is ending right there, the speed of the shadow, of the tip of the shadow, is going to be how fast this length is increasing. So if that's x and that's y, the speed of the tip of the shadow is actually going to be the derivative of x plus y. And here's what's nice about this problem. You should still do it the way we did it. You should still find out how fast the length of the shadow is increasing. And then you can say, well, I want to find out how fast the shadow is moving. It's actually not terrible at all. It's going to be how fast the person is walking plus how fast the length of the shadow is increasing. Or seen another way, if you take the derivative of x plus y, well, the derivative of x plus y is the derivative of x plus the derivative of y. We were told in the problem that the derivative of x, or the rate of change of the person's speed, was 4 feet per second. And we just found that the rate of change of the length of the shadow is 12/7 feet per second. So then you can add those together and get 28 over 7 plus 12 over 7 is 40 over 7 feet per second. Not that I necessarily expect you to see either one of these questions on an exam, but if you did, this is how you would approach it. And they definitely do ask book questions like this, where one way is one way and one way is the other way. All right. So related rates, draw a picture, figure out what's changing, set them an equation, differentiate both sides of that equation, and then plug in the things you know, solve for what you don't, or what you want. Okay, to answer this other question here, so we're trying to estimate the derivative based on a graph that we're given. Was that the thought? Okay. So let me draw a picture here. Try to make it look nice. Sure. Let me give myself some guidelines here. Okay. So something like this. Okay. So there's a few questions we could ask. I could start by asking something like, for what values of x is the derivative equal to 0? Why don't you see if you can write down some answers? I see a few answers. I don't want to hear them yet. All right, who wants to volunteer one of them? Yeah. Sure, 3. What else? Anybody? Yeah.
7.
Not 7, actually. 7's kind of a red herring there. So 7 is not a place where the derivative is equal to 0. Well, actually, 7's kind of important. Where else besides not 7? Yep, and what's the last one? Everybody? Right. So here we have a horizontal tangent line. Here we have a horizontal tangent line. Here we have a horizontal tangent line. Or in other words, in those places we have the place where the slope of the tangent line is 0. So definitely x equal to 3, 5, and 8. On the other hand, what's happening at 7? What is f prime of 7? Well, that's actually not a good question because f prime of 7 doesn't exist. F of x is not differentiable at x equal to 7. How do I know that? Because it's pointy. If you see a pointy point, it's not differentiable there. You don't have a really well-defined tangent line, right? I could try to draw a tangent line like this, or like that, or like that. And any one of those is kind of tangent, although it's not really tangent. It's just kind of going to the point and not touching the rest of the graph. So at pointy points, we don't have a derivative. Now, here's another question. And this is actually kind of leading into what we're about to start talking about. Where does this function, and I failed to label it, where does f of x have a local or relative maximum. And I know we haven't actually really talked about this yet, so we'll just kind of talk about it now. So to have a local relative maximum means that point needs to be higher than all the points next to it, either on the left or the right of it. So I would say certainly at x equal to 3. I know that's what I was trying to say. When someone says where, or when the question is where is this happening, the answer is typically phrased as the x value. It's happening at x equal to this number. So we could say it's happening, we have a relative maximum at x equal to 3 and at x equal to 7. Even though it's not differentiable at 7, you can still see on the graph that it's lower on the left side of 7 and lower on the right side of 7. So it's definitely a relative maximum. And I didn't mean for this to go on forever. I'm going to say that this stops right here. So that's over here at 10. I don't have a good answer about what's happening at 10. So, and what I should say is really what's happening at 10 depends on how people define things. So there's different ways of defining a local relative maximum. Usually we say something about it having to be bigger than all the stuff on either side of it. And if it's not defined on one side, we don't really talk about it. So what I would say here is that I personally wouldn't say we have a local or relative maximum of x equal to 10. Some other people would say you do. And it really just depends on the definitions. It's kind of unfortunate, but it's the truth. Why don't you all answer the following question? Where does f of x have a relative minimum? Yeah. Yes, you may. You can find. So I would probably say that we have a local, not probably, I definitely would say we have a local minimum at x equal to 5 and at x equal to 8. And again, I don't think 1 would qualify as a local minimum because again, it's not defined on both sides. So I wouldn't say that, but again, other people might. So it kind of depends on the definition. But I will point out is question or 5 here, I'll say f of x, and I'll just say instead of asking it as a question, I'll point out that f of x has an absolute or global maximum at x equal to 10. Because that point there, even though it's not considered a local maximum necessarily, it is having a y value or function value that is bigger than every other function value on the page, right? This y value here, whatever it happens to be, that is the highest y value. And then you all should be able to tell me where we have a local, sorry, not local, an absolute or global minimum. I know you all are thinking it. Minimum at x equal to 1. Because just like this point was the highest point on the graph, this point over here is the lowest point on the graph. And then to actually get at what I think your question might have been, although I feel like I kind of went around it, someone could ask, and this is where the question gets hard, is say, estimate the value. Well, it's hard and it's also not hard. Estimate f prime of 2 and f prime of 4. And that's where things get challenging because this is where your graph actually has to be like drawn accurately and you have to do a decent job of estimating what the tangent line looks like. So assuming I've drawn this relatively accurately and my scale is pretty good here, like this is 1, 2, 3, 4, 5, 6. If I try to draw the tangent line right there, let's see what I get. Okay, so I'm thinking I essentially am going from the point 1 comma 3 is about what that looks like. And again, I'm just kind of guessing at it. Let me zoom in here a bit to make this a little easier to see. And over here, I've kind of got the point 4 comma 5. So if I had to guess, I'd say the slope of that tangent line is 5 minus 3 over 4 minus 1. So I think f prime of 2, sorry, I can't quite see that. Sure. Yeah, we can fit it all in there. Yes. Is approximately 5 minus 3, the change in the y values, over 4 minus 1, the change in the x values. So 2/3. It's a decent guess. But again, it's just a guess. And I could have drawn my tangent line more steeply because again, my graph isn't perfect. That was interesting. So what about the other one? What about f prime of 4? Oof, okay. Looking up here at 4. Same kind of idea. I'm going to draw a tangent line and then try to identify some points. And usually when you're doing this kind of problem, it might be like on a grid. So it's easier to like when you draw the tangent line, see what the points are that you're actually almost going through. So if I do that, let's see here. Yeesh. So, And again, this is some guesswork here. I'm gonna pretend like this is the point 2 comma 6, and this is looking like, I don't know, 5 comma 3 maybe. So then my slope would be, oh sorry, you can't quite see that. So this looks like 2, 6, 5, 3. So it looks like I'm going f prime of 4 is, once again, now before I write my answer here, should f prime of 4 be positive or negative? Just looking at the slope of the tangent line here. Positive or negative? Negative for sure. And let's make sure we calculate it correctly here. So it's going to be 3 minus 6 as the difference in y's over 5 minus 2, the difference in x's. That's going to be negative 3 over positive 3, which is negative 1. Sorry, I can't quite see that. Let me zoom back out. I'm getting all trapped up here. And again, these are really just guesses. As long as you're kind of in the ballpark of being right, if they're asking you to do a question like this, you should be fine. Is that kind of what you're looking for? Good, great. Let's see. There's something else I want to say here, though. I know what it was. Oh, that's smooth.
It's for the 5 minus 3.
Sure. So again, and it's kind of hard to see. So this point here, that point is 5 comma 3, and that point is 2 comma 6. So to find the slope of this line, it's y2 minus y1, so 3 minus 6 over x2 minus x1, 5 minus 2. That's where I'm getting the 3 minus 6 over 5 minus 2. But again, your answer could be different because maybe you drew your tangent line slightly steeper or less steep, and you found points that were a little bit different than mine. That's going to happen. That's okay. The other thing I wanted to ask about here is a question again, which is kind of leading into what we're doing next, which is talking about like finding absolute and local extrema and talking about where a function is increasing or decreasing. So where, again, where meaning what x values is f of x increasing? Typically, when we talk about a function being increasing or decreasing, we usually use open intervals. We don't typically include any endpoints. So I would say, well, it looks like it's increasing from 1 to 3 because it's getting bigger as we go from left to right. So f of x is increasing on the interval from 1 to 3. We exclude the endpoints. It's definitely not increasing at 3 because at 3 it's kind of topping out. That's where we change from being increasing to being decreasing. And then we're not going to include from 3 to 5 because it's getting smaller, not bigger. But from 5 to 7, it's also increasing. So we include parentheses 5 comma 7. And then also from 8 to 10. And I'll just point out again, because some books do literally differ in how they write these definitions. It is possible that the correct answer would include the 1 and the 10. Like have a bracket 1 comma 3 and a parentheses 8 comma 10 the bracket. So I'm not usually going to write it that way, but it might be being taught this way in your class, that this could be a potentially correct way of talking about where this function is increasing. But I'm going to say that this is the right answer unless you have strong evidence that I should be doing it a different way. Okay, you know what I'm going to ask next, right? You should, right? You should be able to think about what's the next logical question if I just asked where it's increasing. So you do it. Tell me, and use open intervals. Where is f of x decreasing? You should get two intervals with a union between them. That big U stands for union. All right, let's see. So to me, it looks like it's topping out at x equals 3 and then getting smaller, smaller, smaller until we get to x equals 5. So certainly from 3 to 5, union, and then from 7 to 8. I think there's something else I want to say here. Something else I'll point out, and actually this is kind of an important observation to make. So I would point out that on the intervals where f of x is increasing, you could alternatively say that from x equals 1 to x equals 3, the derivative of f is positive. Think about this. If I were to draw a tangent line on this graph anywhere between 1 and 3, that tangent line would have a positive slope, which would mean the derivative would be positive. So, and this is actually, we're going to use this a lot. If you say that f of x is increasing, that's equivalent to saying that the derivative of f of x is positive. We won't get into it right now, but there's occasionally some very, very, very tiny exceptions for a couple functions I can think of, but they're not super important, so you shouldn't worry about them. Basically, you should equate increasing with having a positive derivative or a positive rate of change, and decreasing having a negative rate of change or a negative derivative. By the way, nobody writes these words like I'm writing right now. No one's going to write this. They're going to say this is just f prime of x is greater than 0, and this is just f prime of x is less than 0. Sure. I know what I was going to say. So, yeah, no, I don't want to say that. Never. I had something I thought was important to say, but it's really not. When you think about a function being increasing or decreasing, you should just think about from left to right, always from left to right. Is it getting bigger? Is it going up? Or is it getting smaller? Is it going down? Or you can think of it as, are the y values getting larger as you go from left to right? Or are the y values getting smaller from left to right? That's what it means to be increasing or decreasing. Sure. So let's go ahead and, as we're moving on here, let's go ahead and look at this important theorem, the extreme value theorem. So here's what it says, and we'll draw some pictures to kind of convince ourselves of this. If f of x is continuous on a closed interval, so something like bracket a comma b with a bracket, then our function f of x has an absolute maximum. You can actually have more than one. You can have multiple absolute maxima, and an absolute minimum. some examples. F of x equal to 2x plus 1 on the interval from 1 to 3. If I plug in 1, 2 times 1 plus 1 is 3. If I plug in 3, 2 times 3 plus 1 is 7. So on this interval from 1 to 3, this function certainly has an absolute maximum. It's this right endpoint here. There's my absolute maximum. Okay, a couple ways to talk about the absolute maximum. You can either say the absolute maximum occurs at x equals 3, or you could say it has a maximum value of y equals 7. But really the easiest way is just to say what the point is. So the absolute maximum is 7 at x equals 3. Or you could say we have an absolute max. And we usually abbreviate absolute with ABS, an absolute max at the point 3, 7. Because that tells you where it occurs and what the value of the maximum is. The maximum value of this function on this interval is 7. Where does that happen? At 3. Okay, and then right here, we have an absolute minimum at the point 1, 3. So the minimum value of this function is 3, and it occurs when x is equal to 1. Questions before we look at some more? I'll point out, it's really important with these kind of problems to make sure you're reading the question carefully, because they'll sometimes ask you for what is the maximum value. Sometimes they'll ask you where is the maximum value. Those are different answers. The answer to where is 3. The answer to what is 7. So make sure you're reading, especially those Weber problems, make sure you're reading them very carefully. Okay, let's look at another example. Let's say we have, sure, f of x equal to x squared on the interval from -3 to 2. I'll point out so far, all of our functions have met the necessary criteria that the function is continuous and the interval is closed. So this function, going from -3 to +2, it's going to look something like this. Where this point over here is 2, 4. This point over here is -3, 9. This point, we can see our absolute maximum is 9. And it happens to occur at x equal to -3. The absolute extremes don't have to occur at the endpoints. They could, but they also could occur somewhere in the middle, like in this one. The absolute minimum isn't 4, it isn't 9, it's 0. So right there, our absolute minimum is y equal to 0, and it occurs at x equal to 0. I'd also point out that for this absolute minimum that's not occurring at one of the endpoints, what's the derivative of this function at that point? Well, if I draw a tangent line, which I've already kind of drawn because it's the x-axis, if I draw this tangent line, that tangent line is horizontal. That slope should be 0. Let's check. My derivative of f is f prime of x equal to 2x. And if you plug in 0, f prime of 0 is 2 times 0, which is 0. So yeah, for that absolute minimum, which isn't occurring at one of the endpoints, the derivative there happens to be 0. That's not a coincidence. It's pretty typical for an interior maximum or minimum to have a derivative that's 0. There's a theorem about that, which we might get to. What about, yeah, let's go back. Sorry, what about, sorry, f of x equal to sine of x on the interval from 0 to 4 pi. What's the period of sine? Ooh, good question. What is the period of sine? Well, if we're going around the unit circle to get one full revolution, what's the angle we go through? In radians. It's going to be 2 pi radians, or 360 degrees. So one period of sine is from 0 to 2 pi, and then we're going to get a whole another period from 2 pi to 4 pi. So here's what it's going to look like. So sine starts in the middle, and then goes up to the top, back to the middle, down to the bottom, back to the middle, and then it just repeats. Goes back to the top, back to the middle, down to the bottom, back to the middle. So here's what it looks like. Okay, so let's answer this question. What value is the absolute maximum? Show me on your fingers. What's the biggest y value we get? Right, it's not very exciting. It's 1. Okay. Better question. How many absolute maxima does this function have on this interval? Right, it has 2. So you can have multiple absolute extrema if you have multiple places where you have the same highest value. So there are 2 of them. One is at x equal to pi over 2. And the other one is over here at x equal to 2 pi plus pi over 2 is going to be a number 5 pi over 2. Similarly, we have absolute minimum values of y equal to -1, and those are going to occur at right here, which is 3 pi over 2, and right here, which is 3 pi over 2 plus 2 pi is 7 pi over 2. So yes, you can have multiple absolute extremes. And they typically occur either at endpoints, as we've seen in the first couple examples, or at places where the derivative is 0. Right? In each of those places, the derivative here is equal to 0. Same deal here, and here, and here. Well, there is one other way we can find an absolute extreme value, or one other thing that could be true where we have an absolute extreme value. So let's look at one more function here. F of x equal to x to the 2/3 on the interval from -8 to +1. All right, so this function, I think I talked about this function a little bit before. I call it the bird function because it kind of looks like a bird an adult man who's not very good at drawing could draw, or a child could draw, right? It kind of looks like that, where it's pointing at the bottom. It's pointing at the origin. So here's what it actually looks like. Did I give myself enough room to the left here? Sure. So it's going to look something like this. So let's see. This point here is 1, 1, because 1 to any power is 1. This point here, which is important, is 0, 0. And this point over here is -8, -8 to the 2/3 power. And I want you all to find it. Find negative 8 to the 2/3 power. It should be positive. This might help. What's the cube root of negative 8? -2, right? Cube roots, you can take cube roots of any positive or negative number, but then it gets squared and becomes +4. So this point over here is -8, 4. So we can certainly see we have an absolute maximum at x equal to -8 with a value of y equal to +4. And our absolute minimum is not an endpoint, it's an interior point. It's at x equal to 0 with a value of y equal to 0. And I'll point out that at that point, the function is not differentiable. It doesn't have these words. The derivative isn't 0 there. The derivative doesn't exist there. So that's the other thing that can be true, kind of like we saw in that first graphing picture we did, right? You can have a minimum either where the graph kind of nicely rounds out and has a nice slope of 0, or where it's pointy and you still get a maximum or minimum that way. So here you can also see that my derivative, which is 2/3 x to the -1/3, here's an important lesson to learn. If I plug in 0 here, what's 0 to the -1/3 power? It's not 0. 0 to a negative power doesn't exist. That's why a lot of the times with this is why for the when we took the derivative of x to the 1/2, instead of writing it as 1/2 x to the -1/2, I wrote it as 1 over 2 root x to really remind myself that there's a place where that function is undefined. If I plug in 0 there, I get division by 0, which is undefined. So I think it's really, really better, especially when you're talking about the domain or where a function is differentiable, to rewrite this with positive powers, to write it as 2 over 3 times x to the +1/3. Or if you prefer, although I don't, you can write it as 2 over 3 times the cube root of x. But either way you slice it, f prime of 0, you're going to get division by 0. That's undefined. So all of this to say, when you're looking for where you might have an absolute maximum or an absolute minimum, you check endpoints and you check any place where the derivative is either 0 or undefined. That's how we look for absolute extrema. So let me write out the words. Absolute extrema, which are just maxima or minima of f of x on a closed interval occur at either endpoints or critical points. And critical points are where either the derivative is equal to 0 or the derivative is undefined. Those are the critical points. Okay, let's see. Sure, let's look at a couple examples. So the reason we're saying this really is so that we can answer these kinds of questions without having to draw the graph, right? You don't want to graph everything you're trying to find an absolute max and absolute minimum for. So, for example, we could say, yeah, find the absolute maximum and minimum value of f of x equal to x cubed minus, oh gosh, forgot what the fuck, oh yeah, x cubed minus 6x squared on the interval from -1 to +7. So here's what we're going to do. We're not going to graph it. Well, we are going to graph it, just not right away. We're going to look at the endpoint, and we're going to also look at any critical points. So we're going to find the critical points by taking the derivative, which in this case is 3x squared minus 12x. And now here's what you're usually going to do. You're going to say, well, where is it equal to 0? Where is it undefined? Now, normally, I wouldn't write this here because I know that my function is never undefined. So if you can look at your function and see that it's not going to ever be undefined, you don't need to think about finding the places where it's undefined. So really, we can kind of just not worry about this in this particular example. So then I set that equal to 0. I try to solve it. I'm going to factor. So I factor out a 3x. I'm left with an x minus 4. So I get two critical points. I get x equal to 0, and I get x minus 4 equal to 0, which means x is equal to positive 4. Make sure your critical points are in your interval. Both of these are. But oftentimes, people will ask this question in a tricky kind of way where one of the critical points that would end up being a maximum or minimum is actually outside of the interval, so you shouldn't even consider it. So if I had said the interval was from, say, positive 1 to 7, we wouldn't care about 0 because 0 isn't in that interval. And we'll definitely see an example in a minute where that does happen. Then step 2, you're going to plug in each critical point and each endpoint to the original function, not to the derivative. And then whichever value is the biggest, that's your maximum. Whichever value is the smallest, that's your minimum. So usually finding absolute extreme values is pretty not terrible. So let's see. There is one thing to make our lives easier, though. So our critical points are 0 and 4, and then our endpoints are -1 and 7. So these are the four numbers we're going to plug into our function. So one of those is really easy. F of 0 is just 0 cubed minus 6 times 0 squared, which is 0. But the other ones are less easy. And so what I would say here is, like, if I'm going to plug in 7, I really don't want to find 7 cubed. It's not that hard, but without a calculator, I'd rather not. I can make my life easier if I factor this function before I start plugging things in. If I rewrite that as x squared times x minus 6, it's very, very much more easy. That's a great sentence, James. Much easier to plug in 7 there and say we get 7 squared times 7 minus 6. We do know that 7 squared is 49, and 7 minus 6 is 1, and 49 times 1 is 49. So if you do a little bit of factoring before you start plugging in values, it's usually going to be easier to find the value you're looking for. Similarly, if I plug in 4 cubed minus 6 times 4 squared it's a bit much, but 4 squared times 4 minus 6 is not that terrible. It's 16 times -2, which is -32. And finally, f of -1. F of -1, you could probably pick either one to plug it into. I'm still going to plug it into the factored one and get -1 squared times -1 minus 6, which is going to be +1 times -7, which is just -7. All right. And then all we have to say is, well, let's see, 49 is the biggest. So 49 is the absolute maximum value, right? Because the question did ask, what's the maximum value, not where is the maximum value? And -32 is the absolute minimum value. That's it. That's all we do. We find the critical points, we find the endpoints, we plug them all into the original function, and then we just say, what's the biggest, what's the smallest? And if there's two numbers that are the same number of biggest, then we say we have an absolute maximum at both of those places. If you're being asked where they are, not what they are. All right, let's see here. Sure. Let's look at that one. Oh, interesting. Sure.
Okay.
Yeah.
Like again, how you would know like if the critical points are Like, you said they weren't.
Sure. Let me explain via another example. Anyways, let's see, let me think here for 1 second. Let me make up something real quick here. 3x 2 times. I'm sure that should work out 3x. Sorry, I just want to make sure this doesn't suck. 2 minus 10. Sure, so let's say our function is f of x equal to x cubed minus 5x squared plus, sorry, minus 8x plus 3. And we want to find, so for f of x above, find the absolute extrema, which just means max and min, on the interval from, let's go say 1 to 5. 5 might be a bit much, but okay, that should work out fine. All right. Sorry, I could do the function there. So for that function, we're going to find the absolute extrema. So we know we're going to plug in 1 and 5. We also have to find any critical points on that interval. So to find the critical points, we're going to take the derivative, which is 3x squared minus 10x minus 8 equal to 0. And then we'd love to solve this. This does factor. So we can use, we could factor it, or we could use the quadratic formula. I probably prefer to factor it. How do we factor this? There's like a whole thing. So the way you factor something like this, where it's a quadratic, but your coefficient over here isn't 1, is you say something like 3 times negative 8, a times c is negative 24, and then your b value is negative 10. So you're looking for numbers that multiply to negative 24 and add up to negative 10. Is that right? Feels wrong. That's right. Are there numbers that do that? I mean, I said the factored, so there should be. My problem is I'm thinking of 4 and 6, but that's not right. Because negative 4 and negative 6 add up to negative 10 and multiply to positive 24. So it's easy to go the wrong way here if you miss the sign. I think the right answer is actually negative 12 and positive 2. Now here's the thing, and I want to make this super explicitly clear. This thing does not factor as x minus 2 times x minus 12. Or the other way, x plus 2. Sorry, I got that. I did something silly there because sometimes I do the wrong thing. X plus 2 times x minus 12. If you multiply that out, you're not going to get that. You're going to get x squared minus 10x minus 24. Not the same at all. So what did we do with the 2 and the negative 12? This is where I always used to really struggle with this. So there's a few ways to do this. Here's what I prefer. I'm going to rewrite 3x squared minus 10x minus 8 equal to 0 as 3x squared, and then the minus 10x we're going to write as 2x minus 12x, or minus 12x plus 2. It doesn't matter which order you pick. So that negative 10x is negative 12x plus 2x minus 8. And now this 4-term thing can be factored via grouping. In the first 2 terms, what's the greatest common factor I can pull out? I see an x and a 3. So 3x times x minus 4 is left over. And now here's what has to happen. Oops. Here's what has to happen in the next step. Sorry, I got too excited there. In the next step, whatever gets factored out, the thing left behind had better also be x minus 4. Otherwise, it doesn't work. But that will happen here. If we factor out a 2, we're left with x minus 4. So then from each of these pieces, we can factor out the x minus 4 and get x minus 4 times 3x plus 2. And now we can find our critical points. One of them is going to come from x minus 4 equals 0, which gives us x equal to 4. The other one comes from setting 3x plus 2 equal to 0. So 3x equals -2, so x equals -2/3. So I'm about to say something that's wrong. Okay, so the points we're going to check are x equal to +4, x equal to -2/3, x equal to +1, and x equal to +5. Now, where's the lie? Which one of those am I lying about? Which one of those isn't in the interval from 1 to 5? -2/3. So that one we do not even care about at all. We don't give it a second thought. It's not in the interval, so that can't be where we have an absolute maximum or absolute minimum for this function on this interval. So that's what I was trying to point out. Sometimes people will do this kind of question and they'll make sure that one of them is outside the interval, and then hopefully you recognize that and ignore it. So then we're going to check those three. So let's see. So I have more over here. Okay, so plugging into this function, f of 4 is equal to, okay, 4 cubed minus 5 times 4 squared minus 8 times 4 plus 3, which is 64, minus 5 times 16 is 80, minus 8 times 4 is 32, plus 3, gross. -16 minus 48 is -45. Sorry, you can't see the -45 very well. So x equals 4, y equals -45. 1 is much easier. F of 1 is just going to be 1 minus 5 minus 8 plus 3. It's a nice thing about 1, whenever you plug it into a polynomial, you just get all the coefficients added or subtracted together. So 1 minus 5 minus 8 plus 3 is going to be -4 minus 8 is -12 plus 3 is -9. And lastly, 5, f of 5 is going to be 5 cubed, which is 125, minus 5 times 5 squared, which is also 125, minus 8 times 5, which is 40, plus 3. So we end up getting -40 plus 3, which is -37. All right. So which of those three numbers, -45, -9, or -37, is the biggest? Right, is the least negative in this context. So f of 1 equal to -9 is our absolute maximum. And similarly, f of 4 equal to -45 is our absolute minimum. Okay, I want to say one more thing in the last 3 minutes we have here. 2 minutes, okay. Plenty of time. So let's say we have this function here. F of x equal to, that's kind of gross, James. Let's pick something nicer. Let's say it was x squared over x plus 1. And I'm interested in finding the critical points. So f prime of x is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom square. And if you simplify this a bit, so this is where we do start wanting to simplify our derivatives, because often we're trying to figure out where they are equal to 0. And to do that, we really have to simplify. So if we simplify this, we're going to get x times 2x plus 1 times 2x minus x squared, leave the bottom as is, and then that's going to equal 2x squared minus x squared is x squared plus 2x over x plus 1 squared. And then we can factor out an x from the top. It'll be x times x plus 2 over x plus 1 squared. Okay, so here's the question I want to answer first. For what values of x is f prime of x equal to 0? I see two values that will do this for us. One of them is 0. The other one is -2. Because if we want this fraction to equal 0, we really need the numerator to equal 0, which means we're either going to get x equal to 0 or x plus 2 equal to 0, which means x equals -2. So those are both critical points. They're places where the derivative is equal to 0. And now here's where you encounter a little bit of weirdness. For what values of x is f prime of x undefined? Everybody, what makes this derivative undefined? We want 0 in the denominator, which means we need x equal to be -1. Okay, now here's the bad news. X equals -1 is important, especially when we graph this thing. Also, when we talk about where this function is increasing or decreasing. But you know what x equals -1 isn't? It's not a critical point. Here's why. It's not in the domain of the original functions. So in the original function, x squared over x plus 1, we would have a vertical asymptote at x equal to -1, which already kind of denies it from being a critical point in the first place. You can't have a maximum there or a minimum there or anything there really, because it's totally undefined there in the first place. We'll talk more about it in the future, but what I'll say is for ones like this where the derivative is undefined, but it's not in the domain, I usually call that a pseudo-critical point. We still care about it. We're still going to put it on our number line when we start talking about where the function is increasing or decreasing, but we need to be really aware that right there, we cannot have a maximum or minimum because we already have a vertical asymptote at x equal to -1. Okay, that's all I have to say for today. I have office hours over in the usual spot. Have a lovely 3-day weekend. I'll see you all on Tuesday. As usual, but don't come to class on Monday. Yeah, you should be fine. Yeah, just keep coming.
How long are you gonna submit like the notes?
So one more time.
Are you gonna submit the notes after this ends? This
So depending on how busy I am in office hours, I usually get them, I can get them posted between like before my next class at 3, but if it's really busy, sometimes I don't get them up until like closer to 5.
okay. And then office hours is at the same place
Yep,
and
over in CADS.
okay. Thank you.
You're welcome. Oh, I didn't see that.